So we're going to look at, to kind of start off today, lots of different types of functions. And we're going to see different variations of these functions throughout the chapter, and we're going to do different things with these different functions. Today's just kind of an introduction into what the basic function looks like for each one of these. And then as the chapter rolls along, we'll keep kind of getting and coming back to these and do different things with them. Most of these I think you've seen before. Maybe you don't really remember what the graph looks like, but most of these, probably more from Algebra 2, you'll at least kind of remember some of the basic graphs and what they kind of look like. Okay, the first one is what we call a linear function, which we talked about in chapter 1. This is sometimes referred to as the identity function because of its basic function, and it's just y equals x. So it's kind of like slope-intercept form, but here my slope would be 1, my y-intercept would be 0. And so if I look at the basic sketch of this, it's just going to be a line. Linear function makes a line. It's going to go through the y-axis, x-axis is 0, 0, and it's just going to continue on. Okay, so a function that we saw in chapter 1. The second one is also a function that we saw in chapter 1. A quadratic function is any function that has an exponent of 2 as its highest exponent. So this one's x squared. Basic shape makes what? Parabola. Okay. Later in the chapter, we'll talk about putting some numbers in here and how does that change my function? Does it shift it left, right, up, down, flip it upside down, all of those kind of things. But the basic, we call that the parent function, or the function that we always compare to is y equals x squared, which is the quadratic function. Okay, the next one is the cubic function. Name kind of tells you what's going on here. We are going to cube the graph, or cube the x. And the basic shape here, I call this the snake-like graph. Notice on these basic functions, they're all hitting or going through the origin in some shape or form, okay? So the origin is kind of like my starting point. And that's the one thing that all of these will come back to. Like for instance here, 0, 0 is the point where it comes down and goes back up. But they all are going to hit as 0, 0 in some way. Okay, this is one you may not have ever seen before, is the cube root function. We won't see this one very often, but they throw it in here today, so I'm going to mention it. It takes the same shape as the cubic function, but it's kind of a sideways snake. So it just basically is taking this graph and turning it. The square root function, we actually saw this just briefly in chapter 1. I know we did a problem that talked about like domain with this. So we graphed it and tried to figure out like what the domain was going to be. This one starts at 0, 0, and is kind of like a half parabola. Just goes to the right. Okay, we got two more. The next one is what we call the reciprocal function. The equation is the reciprocal of x. That's why we call it the reciprocal function. So I just take x, I flip it over, do the reciprocal of it. Okay, and you might remember this one a little bit from Algebra 2. And in all of these, you can put it into your calculator, right? I could type in 1 over x in my calculator, and I could get a basic shape of the graph. And we're just really looking at sketches more than anything. I'm not looking at like plotting points or anything on these today. And you're not going to really do a whole lot other than identifying these today. So that's why I'm not getting real specific with the points. But this would be your basic reciprocal function. It has asymptotes. And asymptotes is a word you might remember. The x-axis and the y-axis are the asymptotes of this graph. It's never going to cross or touch the x or the y-axis. It's going to get really close to it in both cases, but it's never going to cross or touch it. Okay, so in that one, it never does go through 0, 0. So that's one difference on the reciprocal function as opposed to those other ones. And then the last one, we actually saw this one a little bit last chapter also. Is the absolute value function. Okay. The absolute value function is going to make a V. This, I didn't write the equation here, but it's just the absolute value of x. Okay. So really what we're doing here is when I see, for instance, when I see absolute value symbols, I know it's going to be a V every time. We're going to do different things to that function. We're going to add some numbers to it. We're going to do some different things to it. But it's still going to be a V. As long as it has absolute value in the symbol, it'll always be a V. If it is x squared, it'll always be a parabola. It'll always be the U-shaped graph. If it's x cubed, it's always going to be kind of like snake-like graph. So the basic shape will always be the same, but when we add numbers to it, it's going to change the appearance of it a little bit and make it look just a little bit different, other than it'll still be the same basic shape. Okay, so those are just ones that trying to expose you to them. We'll do more with this as the chapter rolls along, but that'll be something that we'll come back to. When I see the square root function, I kind of already know what it's going to look like. Now what's going to happen when I do it? And you can definitely use your calculator to help you out here, right? I'm never going to say you can't use your calculator to help you graph these, but just knowing what the basic shape looks like is a big deal. Okay. One of the things that we're going to do today is do what we call a piecewise function. So this is another function. And this is the one we've never really done before. Well, we're going to talk about how to evaluate a piecewise function, and then we're going to talk about how to graph a piecewise function. And basically, it's a graph that's made up of a bunch of pieces. That's why we call it a piecewise function. So it's not a graph that is all connected together, like a linear graph or a parabola. It's going to break up into different parts or different pieces. The first thing that we're going to talk about is how to evaluate a piecewise function. So I'm going to give you an example of what a piecewise function is going to look like. And it looks kind of different. Okay, we're going to have this like bracket putting this function all into one big set. And it could give me, you'll see some that have like two functions here. You'll see some that have maybe 3 functions or 3 different equations going on here. In this one, I'm just going to start off giving you one that has 2. X plus 4 when x is less than or equal to 1, and then 8 minus x when x is greater than 1. Okay, and we've done evaluation before, where we take a value, we plug it back in, and we see what we get. But it's a little bit different in this case because we have 2 different pieces. Okay, and all you got to remember here is they're going to give us our function notation. And I'm going to ask you to evaluate 4 different values here. And in most cases, what we do is we just take those numbers, we plug it into our function, and we get our answer, right? Well, in this case, it's a little different because we have 2 different functions we have to choose from. We have to decide which one we're going to use. And here's what you have to look at. This tells me the domain for this function. So if x is less than or equal to 1, I'm going to choose this function. If x is bigger than 1, I'm going to choose the second function. Okay? So I'm going to start with -4. -4 is less than or equal to 1, right? So this is the function we're going to choose. We're not going to do both. We're going to do one or the other. And so I'm going to do -4 plus 4, which is 0. That's all you got to do. Okay, and then I'm just going to keep working my way through. Okay, then I'm going to go to 0. 0 is also less than or equal to 1. So we're going to plug it into that first function again. Which is 4. So the math isn't really that hard, right? It's just deciding which function we're going to plug it into. Okay, then we're going to go to 1. Is 1 less than or equal to 1? Yeah, okay, it's equal to, right? So as long as it's less than or equal to 1, that's the function I'm going to plug it into. So I'm going to go 1 plus 4, which is 5. And then for the last one, 3. 3 is not less than or equal to 1. So it doesn't satisfy this, but it is bigger than 1. So now we're going to choose the second function. So now we go 8 minus 3, which is also 5. Okay. So it looks kind of weird, right, the way the function is written, but trying to evaluate, it's really not that bad. The math in itself is not bad. Now, these equations could be quadratic equations, they could be cubic equations, they could be any type of equation. I just gave you some real easy ones that were linear, and when we plug it in, the math wasn't all that hard. But no matter what kind of function I have here, we're just plugging it in for x, right? And if I had, like, let's say a quadratic equation, which was like 2x squared plus 3x minus 4, then I would plug it into multiple x's. Whatever that equation is the equation I plug it into. Let's do one that has 3, just so you can kind of see an example of that one. All right, let's see. Let's do number 20. I'll just make them up here because both of those are from your homework, and I don't want to give you one from homework. So let's say the letter this time is h of x, and the letter that we have here doesn't really matter. Okay. Got your brackets here. I'm going to do x plus 1, 2x plus 3, and 4x minus 5. Okay, and what we're going to do, this is going to be for all x values less than or equal to -2. This is going to be for all x values from -2 to 3. And then let's make this one all x values greater than or equal to 3. Basically, all of your x values are going to be accounted for here, right? Less than or equal to -2, anywhere between -2 and 3. It'd be helpful if I put another symbol in here. And then x is greater than or equal to 3. Okay? And so once again, I could do some evaluation here. I could say, let's do h of -5, h of 0, and h of 6. We got 3 different equations to choose from here. -5. -5 is less than or equal to -2. So here we would just do -5 plus 1, which is -4. 0 is not here. It's not less than or equal to -2. It is between -2 and +3. So this would be 2 times 0 plus 3, which is 3. And then finally, 6. 6 is greater than or equal to 3, so we're going to use this function here, and we're just going to do 4 times 6 minus 5. And that would be 19. Okay. And I could do a ton of them if I needed to, but we're just evaluating for some different values. Okay, so that part is not too bad. Now the graphing of it is going to be a little bit different. And here's what I'll tell you. When we graph a piecewise function, then we are, I'm only going to give you linear functions here. And this isn't going to be something that you're going to be able to put into your calculator. Most of these graphs, I know we like to use our calculator as much as we can. And you could possibly kind of use your calculator here, but it makes, in some cases, I think it makes it a little bit more difficult. So I'm going to try to show you a different way to do it that shouldn't be too bad, hopefully. Okay, and I'm only going to give you, anytime we do a piecewise function, I'm only going to give you linear functions. So we're not going to do all those other weird functions that we started the lesson with. We're just going to focus on linear graph. Okay, so basically this is going to be 2 different pieces. We have 2 different equations and we have 2 pieces. Both of these are linear, okay? And usually a linear equation goes on forever, right? It extends forever, goes left and right in both directions, it goes up and down in both directions. But this graph, we're only going to go up to 3. So we're going to go over to 3 and it's going to stop right there. This part of the graph is going to start at 3 and it's going to go on, okay? So we're going to graph 2 different linear equations on the same graph based on the domain that we have. So here's how we're going to do it. If I graphed this back in chapter 1, we always started off at our y-intercept. And then our slope is 1 over 3. So we're going to go up 1, right 3. I also am going to go down 1 and left 3. Now here's where you got to be careful. I put a point here, and there should be a point here, but we're not including 3. So when I make this point right here, it actually should be an open circle, okay? Because there's no equal to sign here. So I'm going to graph this function all the way up to 3, but not including 3. So now it's just going to be a linear function. I didn't do a very good graph in this, did I? Oh, I know why. Should be right here. That's my fault. I should have only gone down 1. I think I went down 3. I should have gone down 1 and left 3. knew something didn't look right. Okay, and usually this graph would go on forever, right? But we're stopping it at 3 and not including 3. So that's the first piece of my graph. Now we're going to do the second graph, negative x. Now here's the part that's a little bit tricky, okay? Usually when I would graph this in the past, what would my y-intercept be? If there's nothing after the x, it'd be 0, right? And so usually we would put a point at 0, and then my slope is a -1, so I would start at 0, I would go down 1, right 1, down 1, right 1, down 1, right 1, and so on, okay? But we're not going to plot any points to the left of 3. So we got to figure out what are some points. Now here's where you could use your calculator, if I wanted to get some points. And your calculator could be helpful in this instance. So let's take a look. And on this one, it's okay to have a filled in circle because we are including it, greater than or equal to 3. And then I'm just going to continue to go down 1, right 1. Down 1, right 1. And there's my graph. Okay? So it's 2 different pieces that aren't necessarily connected. Okay? They're separated based on my domain. Now, here's what I want to point out to you. Last chapter we talked about a function. What made something a function, especially if I had a graph? How would I determine if this is a function? Yep, all the x values have to be different. Okay, what if I gave you a graph? What did we do if I gave you a graph to determine? The vertical line test, right? As I move my pen across here, right here is the hard part, right? But at 3, this is an open circle, this is a closed circle. That's why this has to be an open circle, because it does pass the vertical line test. Anywhere that I move my pen or my vertical line across this graph, I'm only touching one point at any given time. None of the x values are repeating, okay? So that's why it's still a function. We call it a piecewise function because it's still a function. It still passes the vertical line test. But we'll only pass the vertical line test if I have a closed circle and open circle right here. So that's the one thing you got to be really, really careful of. Okay? So that's a piecewise function. All right, the last problem I'm going to do with you here is kind of a story problem. You may or may not have your book, and that's okay. This is number 9 on page 118. And I'll just kind of read through it. It's a pretty short story problem. We have a fence that has 480 feet of fencing, and we're trying to enclose like a dog park, trying to make a big park for some dogs. If the enclosed area is X feet long, express the area as a function of its length. Okay? So here's the part where it gets a little bit tricky. First of all, we are making a rectangular dog park. And they tell me that the perimeter is 480. And they don't just come right out and say the perimeter is 480. It says the fencing for that dog park. We have 480 feet of fencing that we can use. So another way of saying fencing is it's going around the outside, which is perimeter. Okay? And they don't actually ever use the word perimeter. The area, first of all, is X feet long. But we have to express area as a function of its, I'm having a hard time spelling today, as a function of its length. Okay, so here's how we're going to do this. I want to write the area in terms of x, but we don't know what the width is. Okay? So what we have to do is we have to write the width in terms of x. So first of all, what do I know about perimeter of anything? Perimeter would be what? How would I find the perimeter of any figure? Add up all the sides. Yeah. Okay, we're going to add up all the sides. So we know if I added up all these sides, it's going to add up to be 480. The only thing I don't know is I don't know the width. Okay, they don't give me anything about the width. So for this one here, I'm going to start with y. Okay, y would be the easy one to use. If you want to use w, you can use w. Okay, it doesn't really matter what letter you use here. So I'm going to say x is the length, y is the width. We don't have any numbers that we're using for that, but what we do know is 2x plus 2y equals 480, because we have two lengths and we have two widths. But because we're putting it in terms of length, I have to rewrite this equation in terms of x. So I'm going to solve, in this case, in terms of, for y. I'm going to put y in terms of x. So if I asked you to solve this equation for y, what would I have to do first? What do you think, Riley? Okay, get it by itself. So what would be the first thing that I would move? Subtract 2x, okay? And then we're still trying to get y by itself. So I'm going to divide by 2, and when I divide by 2, I'm going to divide everything by 2, all the way across. So here, 480 divided by 2 would make 240. And here, the 2's can cancel out. So I just have x left. Okay, so this is an expression that represents y. So over here, instead of using y, I could use 240 minus x. Those two are interchangeable. They're the same thing. Okay, we're almost there. I have to write area in terms of its length, which means the only variable that I can use in my equation is x. Okay? Well, usually if I do area, how do I find the area of a rectangle? Length times width. Okay? And so usually I would say x times y, right? I don't know either values. I would just say x times y. If I knew both of them, I could multiply them. I would do length times width. In this case, we know the length is x. But I don't want to use y because I want to write it as a function of its length x. So instead of writing y, I'm going to write 240 minus x. And that would be your answer. Okay. A lot of times this will be written in function notation. And what this simply means is area in terms of x. We're writing our area in terms of x. Is x times 240 minus x. A lot of people might ask me, do we need to distribute the x? Well, you could, but I would say, in this case, there's no reason to. I mean, if you wanted to take it one step further, you could, but I'm also okay with just leaving it like that. Okay. So what we've done here, and where this could come into play, is if this was something I was actually going to do, all I would need to know to find the area of this dog park is know one dimension. All I would need to know is the length. I wouldn't have to find the width. So if I was trying to figure out like what's the biggest dog park I could make, I could figure out like what kind of length could I use, and then I could use that to help me find the width. And so we could kind of work backwards to get there. So a little bit different type of question, writing our answer in terms of a variable rather than just x times y. Okay. Assignment for today. Okay, 1 through 8, all you have to do is write the basic function. You don't have to put it into your calculator, okay? You don't have to do anything else. So if I look at number 1, for instance. Number 1 kind of looks like this. Okay, I'm not getting real specific with the graph, but it kind of looks like this. What kind of function do we have here? Linear, right? And the basic equation for a linear function is y equals x. So that very first page where we talk about all the different functions, you're just going to write the basic function, okay? Obviously, this equation, they tell me what this equation is, negative 2x minus 3, but we're just going to write what the basic function that it's compared to would be, okay? And you can really just go off of the graph or the symbols. Like if I see x squared, it's y equals x squared. If I see absolute value, it's y equals the absolute value of x. So you don't really have to do much on those first 8. Those should be pretty easy. 14 is kind of a story problem, kind of like the one we just did. 19, 20 are evaluation, where you're going to plug it in, and then the last 2 are graphing a piecewise function.